Okay, in this video we're going to look at three rules. First we're going to look at the constant multiple rule. Then we're going to look at the power rule. We've looked at it with positive exponents. We're going to look at it with negative exponents. And then we're going to look at the sum and difference rule. So let's first look at this constant multiple rule. Okay, so the constant multiple rule. So basically for this rule, we're going to take some value, our function is going to take some value, and we'll call that value c, and we're going to multiply it times a function. Okay, so basically if we take the derivative of f of x, that's the same as taking c out front and then taking the derivative of g of x. Okay, let's do a quick proof of this and then an example. So a proof would be something, we're going to start with a function f of x equals c of g of x. Okay, we're going to look at the limit, so the derivative of f of x is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so I'm going to plug x plus h into this function up here. So when I do that, I end up with a limit as h approaches 0, x plus h goes in, I get c g of x plus h minus, if I plug x into this, I'm just going to get c g of x over h. Okay, we see that we have a common value, a greatest common factor of c for both of these. So I'm going to take the limit as h approaches 0. I'm going to take the c out, and then that's going to give me g of x plus h minus g of x over h. Well, with our work of limits, we know that we can take a constant out front. So then I'm left with c times the limit as h approaches 0 of g of x plus h minus g of x over h. Well, this should look familiar. This is the derivative of g of x. So this is simply, I can resubstitute this in and say this is c times the derivative of g of x. Okay, and that was what I was trying to prove. So let's look at an example. If I were to take the function f of x equals 9x cubed. Okay, I've got a power rule, so I can take the derivative of f of x, and remember I can use d dx of f of f of x, or I can use the apostrophe. That's the same notation. So I'm going to take the constant out front. I'm going to take the derivative of x cubed, which is going to be 3, subtract 1 from the exponent, which gives me x squared. So I'm going to get 27x squared is my derivative. Okay, so that's the constant multiple rule. Okay, after we finish the constant multiple rule, now we can look at the power rule for negative exponents. All right, power rule for negative exponents. I'm not going to reprove this because we already proved it in the previous video. We're just going to look at some examples. So if you're working with negative exponents, you can do things like this. Okay, so say you want to take the derivative of 1/3 x minus 1/3 x to the negative 2. So when you do that, you're going to get the derivative, this is x to the 1, so 1/3 times 1 is just 1/3, x to the 0 is 1, minus negative 2 times 1/3 is negative 2/3, x to the subtract 1 would be negative 3. So you might want to clean this up and rewrite it as this. Okay. Another example, you might be given a function in this form, 1 over x squared. And you just want to remember, oh, this is just a negative exponent, so this is really x to the negative 2. So then you can say that's f prime of x equals negative 2x to the negative 3. Okay, so now we're going to get into the final rule, which is going to be this